Lesson 9.4, Normal Distributions. Today we're going to investigate symmetric distributions. A bell-shaped symmetric distribution with a tail on each end is called a normal distribution. Use a graphing calculator and the infant birth mass data in the table below to determine if the set represents a normal distribution. So we have birth mass in kilograms, and it says enter the data into a graphing calculator as a list. Calculate the one variable statistics for the distribution of data. So here is my graphing calculator. To get to the list menu, you click Stat and then hit Enter for edit. And then you're going to enter all of these values in the list. So you'll type in 3.3 and then hit Enter after each one to move down the list. So I'm just going down through the table, entering all of these values, hitting Enter after each one. Again, this is on the app, and it is called Calculate 84. Then once you are finished, you can hit Second Mode, and that will take you back to the home screen. Then to get these data values, we're going to hit Stat, move over to Calc, and then where it says one variable stats, hit Enter, and Enter again. And it's going to give you all of those values on the right-hand side. It might look different if you're actually using a physical graphing calculator. So now we are going to add those to our workbook. It says here that the mean is 3.5. The standard deviation is that little sigma with the subscript x. So in our thing here, you can see the sigma with the subscript x is 0.14. We're going to round down, so just 0.14. The median is 3.5, indicated by that med. And for the IQR, we take from quartile 3 back to quartile 1, and it's that distance between the quartiles. The quartiles split data up into 4 sections. So if we had a chunk of data, the median would be right in the middle, and then quartile 1 and quartile 3 would split it up into those 4 separate chunks. So IQR stands for inner quartile range. It's the distance between Q1 and Q3. And in our calculator, it says that it's 3.4 at Q1 and 3.6 at Q3, which is a difference of 0.2. All right, moving right along, it says sketch the histogram. Always include labels for the axes and the bar intervals. So how many are between 3.11 and 3.20? There is only the one, 3.2, so we're going to draw our bar up to 1. Then how many between 3.21 and 3.30? There are 2 3.3s. And then we have 4 between 3.31 and 3.40. We have 6 between 3.4 and 3.5. Then we've got another 4 between 3.51 and 3.6. 2 between 3.61 and 3.70. and 1 between 3.71 and 3.8. And this is what they mean by a normal distribution. You can see that it's symmetric. If we were to cut it down the middle, it would be similar or a mirror on both sides. It also mentioned that it has that long tail on each end going out towards 0 on each end. So this is considered a normal distribution. So we will say yes. It can be described as a normal distribution. Because it has that bell shape to it. And it is symmetric. With those long tails on each end. Which intervals on the histogram had the fewest values and which interval had the greatest number of values? So the fewest was at the ends. The most was between 3.41 and 3.5, right in the middle. For the normal distribution, the mean and the median are the same. Is this true for every normal distribution? Explain. The symmetric shape indicates that the median will be at the center. It also implies the mean will equal that center value. Now, this is an example of a perfect scenario where our mean came out to 3.5 and our median came out to 3.5. In reality, there might be some slight variation. For example, you might have 3.5 as your median and maybe your mean is going to be 3.49 or 3.48. It's going to be very close. The thought is that they should be nearly identical in a normal distribution. Allison thinks that every symmetric distribution must be bell-shaped. Provide a counterexample to show that she is incorrect. Symmetric just means that if we split it into two parts, both sides would be mirror images of each other. So here's an example of a histogram where they are symmetric, but it's not a bell shape. So here I have the axes. If all of my bars are the same, and I split it in the middle, both sides are mirror images of each other, but it doesn't take on a bell shape. Another example could be if we had two tall, one short, and two tall. Because if we split that down the middle, they are symmetric, they're mirror images of each other, but that does not take on a bell shape either. The bell shape that they're looking for is something like this, a little mountain. Investigating symmetric relative frequency histograms. The table gives the frequency of each mass from the data set used in the first Explorer. Use the frequency table to make a relative frequency table. Notice that there are 20 data values. What is the sum of the relative frequencies? So how many 3.3s were there? 2 out of 20. There were 4 3.4s out of 20, 6 3.5s out of 20, 4 3.6s, 2 3.7s, and 1 3.8. Now, if we add all those up, and you can do the decimal version if you'd like. I'm just going to do the fractions on here because I'm running out of space, but the relative frequency does include those decimals. But if we add all that up, we add the numerators of these fractions, so 1 plus 2 plus 4 plus 6 plus 4 plus 2 plus 1, and that's going to be out of 20. So if we do that, let's see what we would end up with. This would be 3, 7, 13, 17, 19, 20 out of 20. And if we did the decimal version and you add all the decimals together, you would get 1. And it has to add up to 1. That represents 100%. We've included all the data values, and the total out of 20 should be 100%. Now we're going to sketch a relative frequency histogram, where instead of having the heights be how many, the heights are those decimal values or those percentages of the data. So for 3.11 to 3.20, there was 1 out of 20, and that came out to a decimal of 0.05. So we're going to draw that bar in. Then for the next one, there were 2 out of 20, which is a decimal 0.1. For the next section, we had 0.2. Then we had 0.3. Then back to 0.2. Back to 0.1. And lastly, another 0.05. Recall from the first Explorer that the mean of this data set is 3.5 and the standard deviation is 0.14. By how many standard deviations does a birth mass of 3.2 differ from the mean? Round to 1 decimal place. Justify your answer. So to start, we're going to figure out the difference between the mean and that birth mass of 3.2, which comes out to 0.3. And then to figure out how many standard deviations, we need to take that 0.3 and divide by 1 standard deviation, which was 0.14. When we do that, and don't forget to round, we get 2.1. So a birth mass of 3.2 kilograms is 2.1 standard deviations below the mean, because the mean was 3.5, so it's below. Identify the interval of values that are within 1 standard deviation of the mean. Use the frequency table to determine what percent of the values in the set are in this interval. So we know that the mean is 3.5. So if we take 3.5 and we subtract 1 standard deviation, that puts us at 3.36. And then to figure out the upper range, that's 1 standard deviation away, we are going to add 3.5 and then the standard deviation of 0.14 to give us 3.64. So we're trying to figure out how many data values are between 3.36 and 3.64. So flip back to that original chart and count how many are between 3.36 and 3.64. I counted 14. You should include all of the 3.4s, all of the 3.5s, and all of the 3.6 values. And I got 14 out of the 20, which is 0.7, but it asks for what percent. So that is 70% are in this interval. So 70% of the data values are within 1 standard deviation away from the mean. Identify the interval of values that are within 2 standard deviations of the mean. Use the frequency table to determine what percent of values in the data set are in this interval. So we now need to subtract 0.14 twice. And then to find the upper end, that's 2 away, we're going to add 0.14 twice. So how many are between 3.22 and 3.78? So now we need to include the 3.3s and the 3.7s. And there should be 18 out of the 20, which is 0.9. And as a percent, that's 90% are 2 standard deviations from the mean. Using properties of normal distributions. The smaller the intervals are in the symmetric bell-shaped relative frequency histogram, the closer the shape of the histogram is to a curve called a normal curve. Let sigma represent the standard deviation. A normal curve has the following properties. About 68% of the data fall within 1 standard deviation of the mean. In our example, we saw that 70% fell within 1 standard deviation of the mean. Then it says about 95% of the data fall within 2 standard deviations of the mean. And for ours, we had 90%. Then about 99.7% of the data fall within 3 standard deviations of the mean. The symmetry of a normal curve allows you to separate the area under the curve into 8 parts and know what percent of the data is contained in each part. So just some clarifying things here. These little marks indicate that is the mean plus 1 standard deviation. This would be the mean plus 2 standard deviations. And here we would have the mean plus 3 standard deviations. On the other side, since our values are getting smaller, you can see that it's a mean minus 1 standard deviation, minus 2 deviations, and minus 3 deviations. And the reason that they've chunked it out to be 34 and 34 is because they've split this 68 into 2 parts. Then they've taken that extra from 68 to 95 and they've split that up. So now you have 95 split into 2 parts, which is made up from the 34 section and the 13.5 section. So if we add all 4 parts of these together, we should get 95. They're just breaking it up into chunks. Example 1. The mass in grams of pennies minted in the United States after 1982 are normally distributed with a mean of 2.5 grams and a standard deviation of 0.02 grams. Find the percent of these pennies that have a mass between 2.46 and 2.54. Find the percent between 2.46 grams and the mean 2.5 grams. Well, that's a difference of 0.04. It told us the standard deviation was 0.02, and we just found that it was 0.04 away from the mean, which means that that is 2 standard deviations, because 0.02 times 2 would give us 0.04. So to find the percent between 2.54 and 2.5, which is the mean, we would do the same thing. We're going to subtract to find the difference, and we know that that is 2 standard deviations above the mean. So 2.46 is 2 below the mean, and 2.54 is 2 standard deviations above the mean. Well, we know from our discussion earlier that 95% of the data fall within 2 standard deviations of the mean. So down here, 2.46 is 2 standard deviations below, and 2.54 is 2 above. So if we add up all the percentage in between, we should get that 95% of the data in this normal distribution fall within 2 standard deviations of the mean. More specifically, 95% of the pennies minted in the United States after 1982 have a mass that's between 2.46 grams and 2.54 grams. This one is just an example. There's nothing that you need to write down. Just kind of following along. Now we get to find the percent of pennies that have a mass between 2.48 and 2.52. So we're finding the percent between 2.48 and the mean 2.5. So we're subtracting to start out, and that is a difference of 0.02 grams, which is only 1 standard deviation, and that is below the mean because 2.48 is smaller than 2.5. Now we're going to look at the distance between 2.52 and the mean, which is a difference of 0.02. Also 1 standard deviation, but this time it is above. What percent of the normal distributions fall within 1 standard deviation of the mean? Well, here's the mean. This is 1 standard deviation below, and here would be 1 above. If we combine all of those together, 34 plus 34 is 68%. So 68% of the pennies minted in the United States after 1982 have a mass between 2.48 and 2.52. Find the percent of these pennies that have a mass between 2.44 and 2.56. That is a difference of 0.06. And if we split that up into the standard deviations, which are each 0.02, that is 3 deviations away. And that is the same for above. So we got to figure out what percent are 3 standard deviations away. Here's the mean, 3 standard deviations away. 1, 2, 3, and 1, 2, 3. So what percent is between here and here? We need to add up 2.35, 13.5, 34, 34, 13.5, and 2.35 to figure out how much is 3 standard deviations away. That is 99.7% of the pennies are between 2.44 grams and 2.56 grams. Find the percent of these pennies that have a mass between 2.46 and 2.50. Start by subtracting. That is 0.04. Divide by the standard deviation to figure out how many. And that is 2 standard deviations away. So if we scroll back up, it is 2 standard deviations below the mean. So 1, 2. we need to combine 34 and 13.5, which gives us 47.5. So 47.5% are between 2.46 and 2.50 grams. Estimating probabilities in approximately normal distributions. You can use the properties of a normal distribution to make estimations about the larger population that the distribution represents. The masses in grams of pennies minted in the United States after 1982 are normally distributed with a mean of 2.5 grams and a standard deviation of 0.02 grams. Estimate the probability that a randomly chosen penny has a mass greater than 2.52. Find the percent greater than 2.52 grams. So they start by subtracting to find the difference from the mean. And we know that 2.52 grams is one standard deviation above the mean. And then it says shade in the percent of data greater than one standard deviation above the mean. So we're going to shade in more than one standard deviation above the mean. That includes the 13.5%, the 2.35%, and the 0.15%, for a total of 16%. And then they sum it up and they say the probability that a randomly chosen penny has a mass greater than 2.52 grams is about 16%. Now we are going to estimate the probability that a randomly chosen penny has a mass greater than 2.56 grams. So we will start with 2.56. We will subtract the mean, and that gives us a difference of 0.06 grams. And 0.06 grams is 3 standard deviations above the mean. So we will shade in the percent of data that is greater than 3 standard deviations above the mean. So if we went from, that would be 1, 2, 3. So we need to shade in this section, which is 0.15%. The probability that a randomly chosen penny has a mass greater than 2.56 grams is about 0.15%. Find the probability that a randomly chosen penny has a mass less than 2.54 grams. So we're looking for a randomly chosen penny that has a mass lower than 2 standard deviations above. So going back to our picture, this would be the mean, 1 standard deviation above, 2 standard deviations above. But we are looking for pennies that have a mass less than 2 standard deviations above. So we are looking for all of this. Now there's a couple of ways that we can find the answer. We can add up 0.15, 2.35, 13.5, 34, 34, and 13.5, or we can subtract the piece that we don't want from 100. Either way will work, but you should end up with 97.5%. Find the probability that a randomly chosen penny has a mass greater than 2.44. Take the mean, find the difference, which is 3 deviations below, and we're looking for greater than that. Here's the mean, 1 below, 2 below, 3 below, but we are looking for greater than 3 standard deviations below. So we want all of that shaded red stuff. You could also just take this piece off of 100 to figure out the total, or you can add all the shaded red percentages together. And you will end up with 99.85% probability of choosing a penny with a mass greater than 2.44 grams. For data described by a normal distribution, how do the mean and median compare? The mean and median will be equal. Remember, we talked about how if it's nearly a normal distribution, they won't be perfect, but they will be very close. What does the symmetry of a normal distribution tell you about the areas above and below the mean? Well, the area above will be equal to the area below. Or you can think of them as having an area of half, or 50% of the area is above and 50% is below. How can you tell if data follow a normal distribution by looking at a histogram of the data? The histogram has some characteristics that we look out for. We want it to be bell-shaped. We want it to be symmetric. On both sides of the mean. And we want it to have long tails on both sides. How do you find percents of data and probabilities of events associated with normal distributions? We start by figuring out how many standard deviations away from the mean a given data value is. In normal distributions, we know that 68% of data is within 1 deviation. 95% of data is within 2 deviations, and 99.7% is within 3 deviations. Remember that sigma symbol means standard deviation.